All right. This is our introduction to hypothesis testing. It's really the last kind of inference that we need to learn. And it's almost like the last lesson I'll teach you of the year, except that once you get the basics for how this works, it just applies to means, it applies to chi-square, it just goes all the way down until we're done. So what we're looking at is what happens when somebody just makes a claim. And they say something to the effect that, well, at Cinco Ranch High School, about 30% of the students are signed up for AP classes. All right? That's just a claim. All right? That's just saying, this is what I believe the true proportion of students who signed up for AP classes is. We may feel that that's not right, and so we may want to challenge it. The way to challenge it is to come up with some kind of alternative claim and to go after it through sampling to see which one seems to make the most sense. So, hypothesis testing starts by establishing a working hypothesis about a population parameter in question. That's where the starting point is. It's called a null hypothesis, or HO, H naught, and it just means that that is a statement of belief that we're going to throw out there and see if it holds up to scrutiny. The value that we normally give to that hypothesis, which will be a proportion or a mean, or who knows, this will often be a historical value, a claim like I just made, or a production specification. You know, the true average diameter for crankshaft rods is 2.738 centimeters or something like that. And we may feel like, well, maybe they're not equal to that. And so we need to test an alternative. All right, so moving on. So this is another instance of the letter P, so many we've run into. And basically, this is just this is the notation that we use. HO is the null hypothesis, and that is our population parameter P, population proportion P, is equal to some true proportion, or what we think is true. So a television station may claim that they show 20% of their broadcast minutes with commercials each hour. So HO is that the proportion of their commercials is 0.2. Now note, it's an equal, and it's a single number, and no hats. There was no mention of sampling. You should not have a hat on here. We're making a statement about parameters when we write a null hypothesis, or an alternative for that matter. All right? So the population proportion has to equal some true value. This is what they're claiming. All right, any hypothesis that might differ or take exception to the null is called an alternative hypothesis, denoted H with a subscript A. So that is constructed in a way that is the one that we support when we find evidence to reject the null hypothesis. All right, so what if we're a big fan of this station, and, you know, we're just sitting there watching some show and we're about ready to lose our minds because it just seems like the whole thing is just commercials. So we're thinking, right, 20%, we think maybe more. All right? So here are the two competing claims. There's the one from the television station. All right, the P equals 0.2, or 20% of their hourly minutes are devoted to commercials. Our alternative is that the true value is actually greater than that. All right? Now, a couple of things. First of all, no hats. Second of all, do not make this greater than or equal to, right? Because then they're not two distinct arguments, right? They're overlapping. As soon as you put an equal to symbol on here, then you lose distinction between the two arguments, and you're not supposed to have that happen. All right, so this has to be equals, this has to be an inequality. And in a different situation, and depending on how it's worded, it could be less than. It could be not equal to. Like we could say, I don't know about 20 minutes of the hourly, or 20% of the hourly minutes, but I know it ain't that. So we could just put not equal to there. All right, so in order for us to work in normal curves, we need a z-test statistic, and here it is. All right, so that we're in a normally distributed sampling distribution, and all test statistics for these kind of things follow the same pattern. It is sample estimate minus the conjectured value in your HO times divided by the square root, that's your standard error, of P naught times 1 minus P naught over N. All right, if HO is supposed to be considered true, of course we're going to test it, but if the claim is considered true in any way, shape, or form, why would we want to put a P hat value here like we did for confidence intervals? Right? Just take what you have in your HO statement and use that for P. Okay? So P naught is the assumed population parameter. It comes from the HO statement. All right. Now you can do this by hand. We will probably default to the calculator and let it do it for us. All right. So if your null hypothesis is true, what is the probability we would receive the sample result we did, or perhaps more extreme than that? All right, we consider the evidence or sample data, and we reject the null hypothesis in favor of the alternative if there is convincing evidence against the null hypothesis. All right? Now, let me just put up a graphic for you, and maybe this will help you to get it. Okay, so once that station declares that they give 20% of their hourly minutes to commercials, then we can create a sampling distribution, right? And that'll be the center. Well, what happens if we go out and get a sample estimate that will be 0.21? Do you see how close those two things are? Right? So maybe they're only different due to just dumb luck, due to sampling variation, right? That there's no real difference, that we're just seeing a difference just based on the variability that you would get in a sample, right? And I don't know if these numbers are 100% accurate, but let's just say that this much, 0.21 or higher, takes up 0.45 of the curve, or it has a p-value of 0.45. That's pretty good. That's telling you you're likely to see a sample outcome of 0.21 about 50% of the time if this is true. So we really don't have any reason to challenge this HO statement, right? Because our evidence is so close to it that it may just be sampling variation that makes them different. Okay. What if, on the other hand, okay, if P is greater than, we'll talk about alpha in a minute. So here's the same curve, but what if our sample outcome is something way, way different? Like instead of 0.21, it's 0.29, right? And that shows up way far away from what they're telling you, all right? This is very unlikely to just be sampling variation. To see something like this, if the probability of seeing something like that proportion is 0.03, that means we would only see 0.29 as a sample proportion 3 times out of every 100 samples. That's rare. So really, if HO is true, we should not see 0.29, but we did. So perhaps we need to reject HO and look further into it to see what the true value is. All right? So that's what we're saying in that particular slide. Let me get it back up here. If we find convincing evidence from sample data in favor of the alternative, then we're going to reject the null hypothesis. All right, you just saw p-values. You use that z formula to calculate a p-value. Our p-value is the probability of getting an outcome as extreme as, or more extreme than the sample result, assuming that the null hypothesis is true. Now you need to freeze this video and copy this down, because you get asked questions about what's the definition of a p-value, what does it mean? This is what it means. So copy it down and get some working knowledge of it, okay? All right, small p-values are evidence against HO because they say the observed result is really unlikely to occur just by chance. All right, they are compared to an alpha level of significance. Okay, so back to the drawing. All right, I threw an alpha of 0.05, right? It goes up here because we're really looking to see for greater than. That's kind of a right tail situation. And here it is. What this represents, 0.05, this line where it starts, is a cut point. Anything that starts before it is not going to be significant. Anything that starts after it will be. So it helps a new learner with, making decisions. Now you don't need an alpha, and you don't actually need this alpha. It could be 0.01, 0.10, 0.001, 0.1. It could be anything. All right, well, within reason. But 0.05 is kind of common, and see how this test statistic or this sample outcome or higher starts before the rejection region and just overlaps it. That's nothing. That means we're willing to accept that outcome and not reject HO. But 0.05 or 1 sample in 20 is the least that we'll allow before we start to reject. Anything that occurs after that, we're going to reject. So P is less than alpha, we're going to reject HO. P is greater than alpha, we will fail to reject HO. All right? So that's what alpha is. It's just a convenient cut point for you to make a decision, whether to reject or not. And if the problem doesn't present you with a p-value, an alpha value, level of significance, then you can just work off the probability. All right, that p-value is so small that it shouldn't be happening due to chance alone. I'm going to reject HO. If you want, in a situation like that, you can apply an alpha of 0.05 or 0.10 or 0.01, something like that. All right, nothing too extreme. All right, so that's what we mean when we get a p-value that's less than alpha. That's a small p-value. It'll be called statistically significant. In other words, the difference between what the claim is and what I saw in my sample is so different that it's not just due to chance, it's due to some kind of effect. It's statistically significant. It's not just something I can brush off, it matters. So that's just a way of saying that chance alone would rarely produce so extreme a result. All right, if we get a small p-value, we can determine that we can reject HO. If we do that, then we are saying we believe that our results are so unlikely that we're going to choose to support HA. Now, you don't really make conclusions with HA or accept HA. We're either going to reject or fail to reject HO. When a p-value is small, we'll reject it. If a p-value is not sufficiently small, then we will not reject HO. Okay? We're going to keep that as potentially true, right? Because we just don't have any evidence to challenge it. We're actually not claiming that it's true, but we just have insufficient evidence to reject it. Actually, HO could still be false. All right? So, a lot of this is subject to error. We can make mistakes on this without even knowing it. But that's the nature of statistics. All right? We're just going to have to accept the possibility that when we reject things, we can make a mistake doing. Or if we fail to reject things, we can make mistakes doing it. In fact, we have a whole section on error analysis. But the thing is, the probability of our conclusion should be greatly in our favor. All right? So I think that is the last of our slides. So let's go on to the packet notes. All right. This is on page, it starts on page 8. And I'm going to pause this for a moment. I should really have brought the packet so I can read the problem. Hang on, and let's go ahead and hit pause. Okay, so I'm back. So here it is on page 8 at the bottom. Clerk tosses out 2 recall petitions. Random check fails to confirm enough valid signatures was the headline of an article that appeared in the San Luis Obispo Tribune. The article states that a random check of the petition showed that there were not enough valid signatures to force a recall election. For one of the petitions, 11,800 signatures were submitted, and 10,384 valid signatures were required to force a recall election. There would be enough valid signatures to force a recall if 88% or more of the signatures could be verified. The county clerk selected a random sample of 592 signatures and verified the signature, address, and registration status against voter registration records. It was determined that 504 of the 592 signatures were valid. Is there sufficient evidence to conclude that the proportion of valid signatures on the petition is less than 0.88? Test the relevant hypothesis using an alpha of 0.05. Okay. All right, so first of all, we're going to set this up kind of like a confidence interval. They're very closely related, so why not? Define the parameter, and look, I would love to write this all out for you, but I wrote it out 10 times today. So, well, actually 5, but that's enough for me. So if you need to pause anywhere along the line here, then just do it to write. So P is the true proportion of valid signatures on the recall election petition. Great. All right, now it did say that there would be enough valid signatures to force a recall if 88% or more of the signatures could be verified. All right. HO has to be an equal. It does say 88% or more, but I can say HO is that P equals 0.88. Not greater than or equal to, because you cannot put an inequality in the null hypothesis. But what I can say is that 0.88 is the smallest or the lowest possible value where the recall election can go forward. Anything less, HA is that P is less than 0.88, will stop the recall election. So do you see where the decision changes? This recall election, this no recall election. All right? So you need an equals in the null, you need an inequality in the alternative. Sometimes people get goofy and put inequalities in both. And remember, no hats. No hats. All right? So, we were told the sample was chosen randomly. The population of all the signatures is at least 10 times the sample size. And both products are going to be over 10, and you use n times p naught. So n is 592, p naught is 0.88, and you get 520.96 for one product and 71.04 for the other. The two ought to add up to 592. They always do. So both exceed 10. So the normality of the sampling distribution is approximated. Now you will need these first three in your write-ups. You do not need number 4. You don't need this. All right, drawing a model curve will just help you to visualize the geometry of the process. So here's your sample. P hat is 504 over 592, or 0.8514. All right, and here's a curve. I'm going to center it at 0 as though everything had been standardized, and 0.05 is the proportion or the probability for my alpha. Alpha is 0.05. So, and I should have put an alpha here, sorry. That is your rejection region. And so anything that's in here that starts and ends in here is going to be causing us to reject HO. All right. Now I did draw something in, but normally we would wait till we get results. All right. So the next step you do have to do, but you don't have to show the math like this. All right. I'm just showing you where things come from. So you get a z-score. That's going to be sample estimate 0.8514 minus p naught 0.88 divided by the square root. That's your standard error of 0.88 times 0.12 over 592. That will give you a z-score in your sampling distribution of 2.1414. That's more than 2 standard deviations away from the mean. That's kind of extreme. So we'll see if it translates into a p-value that's less than alpha. So name this results for a one proportion z-test. You can go one prop z-test if you want. And this is going to be negative infinity up to this z value. All right, so normal CDF, negative 1,000 up to 2.1414, and you get this, 0.0161. That's going to be less than your alpha, right? Alpha is 0.05. All right, but we'll get to that. Now this, calculating that z value and doing normal CDF are fine, but I would just revert to the calculator on this, all right? So go to a calculate page and do menu and statistics and all the way down to stat tests and one proportion z-test. There it is. All right, the P-naught statement here is 0.88. The number of successes was, I believe, 504. That was the numerator of our fraction. And that was out of 592. So that'll be n. And this one, if you remember, let's see if I can pop this up here, was less than. That's our alternative. So we got to make sure that this is the correct alternative. That is not equal to, so that is not correct. All right, go in there, right arrow, drop down to less than, hit enter, tab to OK, and you're good to go. All right, so you need to write down the z-score, this. You need to write down the p-value, this. And you need to write down the p-hat value, all right? That's 0.8514 rounded. If we go to 0.016, that's about what we got by doing it by hand. There were some rounding issues in it. That's why they're a little different. And then the z is negative 2.145, all right? So there they are. So you name your procedure and you write down these things. And you can put the alpha in there with it. Okay, there it is. So compare p to alpha. P is less than alpha. So if you draw it in there, see how that is a smaller piece of that overall rejection region? And there's nothing on the outside. So p is less than alpha, 0.016 is less than 0.05. We are going to reject. So here is the script for your rejection. Since p is less than alpha, right, you do that comparison. The results are significant. That's important to say. And we reject HO. So one sentence, three things. Compare p to alpha, say if it's significant, and then say what you're going to do about it. Then you can finish up with something in context. There is sufficient evidence to believe that the proportion of valid signatures on the petitions is less than 0.88, and you can say 88% because that's the way they were communicating it in the problem. If you have any problems with your assumptions, which we didn't, you can put your limitation statement here. However, violation of the blah 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 condition may render this result invalid. All right, but we didn't have it, so it doesn't need to go there. So there it is. That's how it works. That is a one-sided test because we did all our work on the left side. You can have another one-sided for greater than, which would put all your work on the right side. But what if you're just going with not equal to? Not equal to is the next one. And that will be two-sided. See two-sided? And there's a key word that usually pops up that'll allow you to know when you have a two-sided alternative, right? In the problem, Associated Press reported that 71% of Americans 25 or older are overweight. Suppose that an investigator wishes to know whether the proportion of such individuals in her state are overweight, differs, right? That is the word right here. It is right there, differs from the national proportion. It's not saying, is it bigger? It's not saying, is it smaller? It just says, is it different? Because it could be either one. All right, so a random sample of 600 people found that 440 are classified as overweight. Is there evidence to suggest that the proportion of individuals in her state who are overweight differ, okay, there it is, from the national proportion? use alpha is 0.10. Okay, there's a different value. Here we did 0.05, right? If we do 0.10, you're going to have a bigger rejection region, so you don't need as much evidence to reject HO with some alpha value or critical value of that amount. So anyway, define the parameter. P is the true proportion of overweight Americans 25 and older who are overweight in this state. All right, they're either the same as the national, no different. That's usually what a null is. It's very conservative. It's no change, no difference. HA, the alternative, is not equal to, because we're seeing if it's different. That's going to have some kind of effects on how we calculate things. All right. So sample is chosen randomly. The population in the state's probably pretty big, so it's at least 10 times the sample size. N times P naught is 600 times 0.71 or 426. And I left the naught off. You can do that if you want. And then N times 1 minus P is going to be 174. So both exceed 10 and you're good for normality. Okay? All right, model curve. So I drew this. Remember, your alpha is 0.10. You have to split that in a two-sided, because it could be that you're different from HO going up, or it could be you're different from HO going down. So here's 0.05 here from the dotted line to the right, and here's another 0.05 from the dotted line to the left. Those are your rejection regions. Okay? Yeah. So you can't just put 0.10 here and 0.10 here, because then alpha becomes together 0.20. And that actually is going to increase your probability of getting an error in your result. So you don't want that. Here's P hat, 0.7333. Okay, so I'll come back to the drawing. Z is going to equal your sample estimate minus your P naught divided by the square root of P naught times 1 minus P naught over N. So there it all is. And you get 1.259, which is not really extreme. So I'm going to put 1.259 here. I believe this will be 1.96, so this is closer to the middle. But you also have to assume it could go this way. So that's negative 1.259, okay? And neither one of those is starting in the rejection region. Yes, when you color it in, they overlap, but it's got to be totally in there for you to reject. So I don't think we're rejecting this. All right, here's the other issue. Since you're going to compute, this probability and this probability, it's really going to be twice either one of them separately. So twice normal CDF, and I'll just do this end here. 1.259 to 1,000 is 0.2080. Okay? And from the calculator, let's just jump over here. And we'll just do another menu. Statistics, stat tests, one prop Z test. I believe that this should be 0.71. All right. I believe this was 440. All right. And I believe that N was 600. And remember, the default position for the alternative is not equal to, and that's exactly what we want. Now the calculator will double the p-value for you. So whatever comes out is ready to go. All right, so record Z, your p-value, and your p hat value. Again, it should be a little bit different. Ooh, wait a minute. Is this the other one? Yeah. I thought it was supposed to recalculate. Well, let me go back and figure out what it did. All right, maybe I put in the old values. Silly me. Can't have that. So let's give it another shot. All right, so 0.71 and 440 and 600. And we can tab to OK, hit OK. All right, here we go. All right, here's Z, here's P, Here's your p hat. Those are duly recorded here, here, and here. All right, so compare p to alpha, 0.2078 and 0.1. All right, p is greater than alpha. So since p is greater than alpha, your results are not significant and we fail to reject HO. So don't accept HA or anything like that. We're either rejecting or failing to reject HO. Here we will fail to reject HO. So there is evidence to believe that the proportion of overweight adults in this state does not differ from the national average. So we're saying the difference between here and here is just due to sampling variation. All right, it's not extreme enough for us to choose to challenge that null hypothesis. This is what we covered. So go ahead and do the assignment, the 1 through 4. I can't remember what page it's on, but you'll find it's in the calendar. And give it a shot. This you'll get better at the more you do it. You'll get quicker at it the more you do it. The writing gets to be a drag, but this is something that you may one day get paid for, so you're going to want to do a good professional job, which is what I'm teaching you. So on that note, I'm going to close out, and I will see you when I see you.